Welcome! I'm Simon, and in this video I will teach you quantum hardware design, and we will focus on RFIC chip design. So here's a structure: 30 minutes theory, introduction to early theory of designing RFIC circuits, and then we will move to layout, simulation, designing circuits, and evaluating it. Now, here's the usage in different quantum computer types. RFIC circuits or RFIC chips which support cryo operation can be used in spin qubit and superconducting types. Here's quantum computer architecture. In this part, we will focus on the third part, which is HEMT or RFIC cryo part. It is typically 800 millikelvin. So here is our main component for our RFIC chip, which is capacitor. We can use interdigitated capacitors or normal planar capacitors. Interdigitated are better because they have, I think, higher capacitances. So this is the first component. The second component is on-chip inductor, which is spiral inductor, and it has two leads. And the spiral, we can calculate our inductance using some online calculators, like the online ones or Saturn one, I think, where we pass number of turns, width, and a few other parameters, and it will calculate inductance for us. There is another component which is quite similar to inductor. This is transformer. We have you can see two leads which are differential in some cases. Like oftentimes it's differential. So we have two differential leads and two differential leads on the other side, and then we have like other coil in different metal layer. So this is very common, used for isolation and kind of conversion of our signals. Those are also called balloons, which are symmetrical, and those are just balancing transformers. So there are types of transistor technologies. First one is bipolar, which is a very common one, very old one, simple. When the transistor is small, it can be used for quite high frequencies. Now it's quite simple, it's cheap, and it's used for low noise amplifiers. There is also CMOS technology, which is newer technology. It has parasitic capacitances, and it is used for high frequency power amplifiers. And there is technology which is called bipolar CMOS technology, which is hybrid technology, and it combines both of two worlds, and it uses advantages of each technology. So this is used for very high frequencies, and it is very reliable and stable and very popular. So it can be used for even like 20 plus gigahertz, and it can carry quite a high currents. So it is very nice technology. So there is RFIC chip preview or overview of LNI dies. The first one is LNA, you can see inductors, and here is some capacitor. You can see the plane here, or rectangle. This is capacitor, and this is our transistor. So we have probably 5 transistors in a row, and quite a simple CMOS LNA chip, or 4 transistors. Uh, Quite simple LNA chip. You can see even dimensions. It's quite small. It is uh, 300 micrometers or so quite small. And here is more advanced CMOS LNI amplifier. You can see more spiral inductors. You can see more connection pins here. So it means it uses more transistors, and it also uses uh, some voltages for biasing these transistors. So some transistors are really used to bias um, the LNA or the chip. So this is more advanced one. So here is evolution of MOSFET technology. You can see mm, different kind of types of mm, usage of drains and sources and doping and all kind of dimensions. You can see this is 130 nanometers, and there are smaller nodes, and you can see different substrates, and you can see different materials used for the gates and stuff like this. And in the end, you have a very advanced and very small node where you need to really use FinFET technology for really using your transistors at this speeds. So there is really explanation of the structure of our transistor and different materials used. Um, so there is a comprehensive breakdown of devices. We either have bipolar, and it breaks down to classical BJTs and heterojunctions ones, and then we have our unipolar transistors, which is just MOSFET. LDMOS is quite popular for RF power electronics, and then we have our HEM technology, which is oftentimes used for radar technologies and stuff where you need really high frequency signals. So there is breakdown of different technologies. There is a technique to really lay out your CMOS transistor. You have your this is your transistor when you look like you're designing it. I mean, those are pins for this, and there is I think gate connection, and what we can do is really split these transistors and kind of multiply them and add multiple gates, and this is called fingering, and you can really lower the resistance, uh, but you will slightly increase capacitance, I think. Um, this is the technique used for some high frequency circuits, I think. Um, So there is kind of understanding of network devices or S parameters, how these things work. We have S parameters, input parameters, and output parameters. On the other side, there's S1 port and like this is S11. This is the first pin, and this is the second pin. This is like our input signal, and this is our reflection. This is S22, and this is really kind of reflection. There is I think uh, there is output to the signal, there is output to the load, and there is, I think, reflection or something. Yeah. um so this is our S matrix, and from this we can really um, make impedance profiles and stuff like this if we want to. This is very important thing. Here is our amplifier in the middle, and in order to work very well and at the maximal performance, we really need input matching network. So mm, all the power we want to deliver to the amplifier that gets amplified and not reflected, so it's matched at a specific impedance, preferably 50 ohms, and it is matched at the output as well. So the amplifier is also um, just working at this maximal performance and stable and everything. So here is our Smith chart. It really tells us mm, kind of how our circuit operates. There is open circuit on the right here, right side, and on the left side there is short circuit. Upwards there is inductive element, and downwards there is capacitive element, and here's our trace for our um, kind of trace in different frequency sweeps or different frequency spectrums. So here we can really track our mm, signal across different frequencies. So this is a very important thing, Smith chart, and from here we will know our um, impedance of a circuit. There is another very important thing for amplifiers and RFIC circuits, which is called third order intercept thing. Here is our input power in dBm, and here is our output power. And if we increase our input power, our amplifier will amplify. But once we reach certain point, it will just kind of to call it bias itself, and it will start compress the signal and it won't amplify anymore. It will just yeah, it won't amplify the signal anymore. It will only amplify, I think, noise. So this is really our understanding of input against output signals, and how it really works. So here is simple schematic of low noise amplifier. It uses bipolar transistors with inductors. Here is our input signal. Here is our um, transistor, and here is our um, inductor choke or something. I think it's called RF choke. And here is our output signal. It is a very simple and straightforward circuit. It is often used for prototyping and simulations and really understanding how the LNA works. It does require only one power supply, oftentimes, um, and it does not require any power sequence compared to more advanced CMOS integrated circuits and LNAs, which typically require power sequence. So here's our more advanced CMOS amplifier. Notice differential pairs. Um, this is this can be quite a problem because you might need to use some balancing transformer to really convert your signal if you have only one input signal. But if you have device where you have like differential pairs, differential signals, this can be really advantageous because um, it is better for transmission. Um, you can see it uses CMOS technology. You have a lot of transistors and you have a lot of uh, biasing circuitry. You have mm, multiple bias ports, so you would require power sequence. You can see it uses quite a low voltage for supply, for power supply, and it is in quite common node, which is 130 nanometers, so it can be manufactured by a lot of foundries and you don't require any very advanced and very special foundry. But on the other hand, it won't run for extremely high frequencies. So here's our high frequency equivalent of transistors. You can see you can break down your transistor into lumped elements representation, and you can exchange um, some components for some current sources, and you can simulate this, and from this you can really um, see parameters of a circuit. So here is our parasitic capacitances for RF stuff. This is very important because it is main limitation in very high frequency circuits, which go um, more than probably or oftentimes 10 gigahertz plus. So the capacitances is a big obstacle. So we need to keep this in mind when designing circuits to pick a great model of transistor. So you can really use it in your RFIC circuit. We should keep capacitance low as possible, and the circuit itself should be as small as possible if we want to run for very high frequencies. And we need to work with capacitances of our substrates, so we pick proper substrate for our chip and we know it will be able to run for very high frequencies. So there are some circuits which require many metal layers. And this is for more advanced chips. You need vias and interconnections, and at the same time, you need to keep your circuit as small as possible. Or just inductors does not fit into one layer, or you require kind of connecting your inductors or your transformers or balloon transformers. So you need multiple metal layers. So there's our metal kind of stack up for RFIC circuits. And here is breakdown of different substrates for different types of frequency chips. The first very common one is silicon, which is now very popular for normal circuits, but this is very slow. Mm, there is gallium arsenide, which is very popular for high electron mobility transistors. There is gallium nitride, which is for high power RF circuits, and there is indium phosphide, I think, which is for microwave circuits, which are very, very fast. And those are probably 100 gigahertz plus thing. So this is our different substrates breakdown. And here is our workflow. You will start with concept, the same with the quantum chip design. This is very similar. Then you need to do lumped elements representation, where you put your transistors and capacitors and inductors, and then you jump into simulation. Then you need to do layout of the RFIC chip, and then you might need to really simulate some properties of the layout, so you can export it into some FEM simulation and really simulate the real inductance of the on-chip inductors, so you really know the calculation using your tools, your online tools were correct, and you will actually get your RFIC as desired. And then the next step is fabrication, where you actually push your RFIC chip into some foundry, and they will actually manufacture it for you. And here are different circuit simulation tools. Just forget Josephson circuits, which is only for a quantum traveling with parametric amplifiers. But I want to highlight that you can use similar tools like Keysight and AVR for your circuit simulation of RFIC chips. And here are FEM simulation tools. You can use Ansys or Elmer or Palace. It's your choice. Each has its own positives and downsides. And here are FEM simulation types. Um, you can really do scattering matrices and impedance and S parameters, which is very common and very advisable. Then you might need to really push it into FEM simulation and do really some simulation of fields, and then you might need to do capacitances and inductance and really see the capacitance of the substrate is correct, and the capacitance of the like each point of a circuit. So this is our FEM simulation. This is fabrication materials. You also have some top metals, bottom layers, and substrates. For substrates, we already talked about silicon, gallium arsenide. It's your choice. Uh, you don't have insulating layer for Josephson junctions. We don't use Josephson junctions here for quantum chips. And here is our fabrication process. It starts with spin coating, exposure to AUV, and for this you use ASML machines. Then you have development of the circuits, etching, and when it's etched, you need to coat it and metal fill it. For fabrication, you might use global foundries, which is very fine for 130 node, and they work with a lot of different types of mm, substrates, so it's fine. Some tasks or book to follow. There is Microwave Engineering by Pojar, which is more theoretical, and there is RF CMOS circuits by Razavi, which is more hands-on and more kind of about actual design. So if you like my work, please feel free to contact me either on LinkedIn or Gmail. So this is really our schematic in AVR, which is free trial and everybody can download it and gets hands on it. So this is our really schematic of our RFIC LNA chip. In order to get here, you can follow the kind of guidelines from previous tutorials where we defined our schematic, but we can simply and quickly do this right now. So once you open your new AVR page, you can click new schematic, create new schematic, and you will have a blank schematic. Then you jump into elements tab, pick some library you wish to use. Now we use this one, and then we will add components. We need to pick the proper transistors and proper um, kind of technology so you can really manufacture it. So if you have PDK, you need to import it here and really use your PDK so it is manufacturable with your library. So this is our first transistor. We can copy this one and add a second one. We also need two more, so we uh, um, I'm sorry, it doesn't. We need two more, so we can copy and paste it. So we have two more now. Now we need to add inductors. For inductors, we just simply need to click spiral inductor and add one spiral inductor. We can click and rotate it. We can do this quickly by clicking here and rotating it. So we have one spiral inductor here and one here and one here. We also need two more. So we just add it here. So this is our spiral inductors, and now we need to add capacitors. So for a capacitor, we need to really add one capacitor here and mm, mm, copy and paste it. Then click rotate and rotate it. Now we need to connect the places accordingly. So let's just connect it. Um, so here is our kind of layout for this. Now we need to kind of connect it here and here. Now we need to add grounds. So in order to create grounds, we need to click. We need to add it here. So this is really our ground. We need to connect transistors to the grounds. So we can copy and paste it. So here is our connecting substrate of the transistors to the ground. Um, so um, it's quite simple and straightforward, very quick. Um, so this is really our schematic right now. Then we need to kind of add some resistors. So let's just, I'm not sure about this one, so I can go back and see the reference. This should be nval, and we can really go back to schematic 4 and uh, pick the nval because it's very high. Um, because it's very high resistance, so uh, it's just this technology. Um, for different kind of resistance values, you can see there is a poly resistor which is 5 ohms per square. Not sure, micrometer probably. And 100 ohms square is endo polyresistor, and an nval is 1K. So there are different types of resistors, and each resistor kind of differ in its properties. Some are more precise, and they just have different behavior. I recommend looking up some book to really know the properties of different types of resistors. It is really helpful in chip design. So now we can really assign ports. So for the assigning ports, we just click here port and assign port. Um, we just need to rotate it here. So now we have our ports assigned. We can like once we transform this into design, we can really change the port for different layout model. So we can really click library name here, and if we just choose the correct thing, we can really assign this some layout modeler representation for our kind of situation, or for our, in our case we just click rectangle pin, and this will create the rectangular pin port in a layout. So we do just this, and for um, 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 uh, for our um, bias, we can just um, add this contact here, and it will create I think via for us, if I'm correct, or it will connect to the mm, ground, no, substrate, not sure, but I know that in previous this might be the via, I think, because in previous reference schematic we have this one. Um, so yeah, this is really that are substrate um, and we assigned it um, hmm, default. Let me just um, if I choose the proper one, probably not. So one of these should really work, and we need to connect this to the ground, and this is uh, let me search for the reference. One of these two should work and should um, maybe the previous one. um, yeah, now it's as it should be. So this is really connection um, to the ground. So yeah, now we just need to assign proper values. So if we just click view and view layout, you can see all the inductors are same, and this is just not proper value. So we need to go back and really assign the different values for each inductor and capacitor. Um, so um, we can just maybe show the um, we can just show the one example one, and uh, really let me we can maybe just show the first one inductor, how it really changes, and then really export it. The only thing which I changed here is number of turns, so this should be quite straightforward. So view layout, and now I think when we um, so this is our really the small inductor which we changed. So you can see it really changes accordingly. So here are our uh, our components, and we also need to change the transistors uh, so they will have mm, more gates, so it's easier to work with them, and they are suited for the RF design. So this is really our um, pin contact, which we defined in port. This is something we changed in port. Like once we clicked on the port and we assigned it a layout model. So this is really our layout, and I'll just try to change uh, the values and the numbers, in the layout accordingly, and then transform it into layout. So here is our layout. I assigned more ports. I just added more ports in the schematic, and then I assigned it a layout model for each one, and then arranged it so it is in nice rectangular pattern, so we can create a nice kind of gauge for this. I also changed the inductor values and then placed them so they're in the right order, so it nicely matches schematic. Then I changed the values for the capacitors, so this is really our capacitor. This is our transistor, um, and there is our connection to substrate, and this is really all we need. So now we need to connect our mm, uh, our pin port to inductor. You can see it needs connection because there is a red line which highlights there needs to be a connection. We can double click it, and once we double click it, it will open up menu to really create a connection for us. So we can double click it again and just drag the pad or layout line, and it will create a connection for us. Once we double click it, we can see it will create a device and connect the pin port, which is material poly, and it will create connection to the metal inductor. We can see we work in metal 4 layers. In this menu, we will see all the layers we need. We will work with different metals for different connections. So this is really the simplest connection to our inductor. We need to do the same thing for connecting um, for really connecting the other the other types. Now we really need to um, mm, we really need to mm, connect the transistors. So we can do this by uh, mm, clicking on the line, and now we just need to we just probably need to change the route dimensions. So we need to somehow go to show routing properties, and here we need to change it to 0.5 and 0.5 here, and we can also change the metal type. So for this we will choose metal 1, for example, and now we can close it, and now we can just draw it and see it really works. So let me do it one more time, um, and now you can see there is a connection, and you can see there is no need for vice since we are on the same layer type, and this way we can connect all the this way we can um, um, connect all the um, we can connect all the connections required, the transistors So just keep in mind we need to change the show routing properties. So this is really connection our transistors. Now we have our resistors. So we need to do the same thing. We just double click it and connect it to the capacitor. Um, Once we have all the connections, it will look like this. And now we just need to create add path and create a kind of um, cage around the chip, which will look like this. And we need to click shape properties and use let's say metal 4, and let's change the path properties to 3. So this is really how we kind of set boundaries for the chip. So this is very simple. Now we need to draw a polygon, and polygon will be from different materials. So we need to kind of we kind of need to select it here. So draw polygon, and let's just um, um, create a polygon here, and this is our really grounding. And we need to do the same thing on the other side. Um, mm, mm, I'm not really sure about the resistor connection. Mm, so it should be like this probably, or probably like this. Yeah, this should be quite okay. So this is our finished RFIC chip. We can now create GDSI files and push it to production, I think. One more thing we can do here in a schematic is to really assign two ports and add inductor in the middle and assign its turns, width, and spacing and diameter here. And once we have all the properties assigned, we have our small schematic, and we can really go to graph, add new graph, and it will create the graph for us, and we can create new measurement, add measurement, and here in schematic we can just go to linear uh, LSRL, and here we can really assign a schematic and port index and frequency sweep. Click OK, and it will create a plot where we can really evaluate our inductance, because here we only set the dimensions here, so we won't be able to see the inductance of the inductor. So here we can really simply in the simulator evaluate the inductance if our um, online calculator which we used uh, is working. We use online calculator for mm, spiral on chip inductor uh, mm, um, here. It's quite simple and made by Stanford University. It's very simple. You just um, pass the turns with spacing and diameter. So we can just add some random values um, and click calculate, and it will calculate the values for us. So this is how you really simulate your inductor. So there is a 3D layout or representation of our RFIC chip. We can see the different layers and different kind of types and components here. So we can see our ground plane here. We can see our mm, line to set the boundaries for the chip. You can see our inductors here. Inductors are metal 4, which is the highest level metal. I think you can see our ports here, and you can also see there is our capacitor. This is our capacitor, and this is our MOSFET transistor. So you can see all the components visualized here. So this is nice and helps to really see all the components here and see the structure of whole chip here. Um, so it really helps when you're designing something and not sure about layers and how to really put it together and make it work. So this is really how you view your RFIC chip. Now you might need to really see some simulation of the amplifiers. So I added some example LNA amplifier, which is already model in the AVR. So some total random example amplifier. I just added 2 ports in new schematic. And so this is really our amplifier. We need to add 2 ports which are 50 ohms impedance matched. In some cases you might need to add kind of power supply which is like this power supply, and for the voltage we might be able to set, let's say, 3 volts, and you need to connect this one to ground, which would be like this, and this port you would need to connect to the supply voltage. So this is for some scenarios. So in our case, we have our LNA amplifier and 2 ports. We just need to go to graphs, new graph, rectangular, add measurement, schematic, port parameters, all sources, schematic, and then add dB, and then we need to mm, kind of set the proper frequencies for us. In our case, it should be okay. If you need to really change it, we can go to um, options, project options, frequencies, and we pass the frequency, which will be uh, maybe from 1 gigahertz to 10 gigahertz, and step should be 0.1. Apply, and this is really our frequency. Then we click this simulate option here, and we can really see our plot. So this is S11 plot. We might need to see the gain plot. So this is really the gain plot, and we can see now we have mm, like 6 dB on 5 gigahertz for our amplifier. So this is like total random amplifier um, which I choose. So I won't really kind of mm, examine the output of graph or measurement. I'll just leave it as it is because I don't really care about this. I just wanted to show how you really set up your simulation and how you really prepare it for simulating. So this is really kind of how you really wrap your model, your whole kind of layout with transistors, capacitors, and inductors into one model, and then kind of assign it a symbol like this here in symbol. You just assign it a symbol here and just add one port and output port and assign frequencies and run the simulation. Oh, and that's a wrap. One more thing, if you have something to say, please feel free to contact me either on Gmail or LinkedIn. Thank you.